right now, millions of Americans are literally closing their eyes and trusting their deepest mental health struggles to a voice that does not exist.
Yeah, a voice with no lungs, no heartbeat, and frankly, not an ounce of actual biological empathy.
Which is just wild from a user experience perspective. But,
Yeah.
we want to welcome you to today's deep dive where we are going to unpack exactly that.
Right, because historically, when you hear a tremor in someone's voice, there's a biological causality to it.
Mm,
Like fear or sadness physically tightens the vocal cords, it alters the airflow.
yeah.
You're hearing the real physiological reality of another person's
But
consciousness.
when you strip all that biology away and just replace it with code, you're left with an acoustic illusion. And that illusion is our mission today. We are tracking the evolution of emotional text-to-speech.
Moving from those really flat robotic computer voices of the early 2000s
Mm-hmm.
right up to modern AI that can literally sigh, hesitate, and adapt to your mood in real time.
Exactly. And as a UX designer, I look at this stuff and I constantly wonder, how do we actually engineer a feeling of trust into an interface?
And, well, as a tech analyst looking at the system architecture, the sheer algorithmic gymnastics required to fake that biological causality is just staggering.
It really is. So to figure this out for you, we've pulled a pretty deep stack of sources. I've been digging through the new 2026 Meditation Statistics Report, alongside some really dense technical documentation from Amazon and Google.
We're also pulling from a few recent human-robot interaction studies, plus some cutting-edge academic papers on these massive new AI voice frameworks, specifically PeriEvits and the Moon framework.
Right, and the goal here is to understand how developers are trying to bridge this empathy gap in synthetic voices. Like, why does slapping a screen into a cute physical robot sometimes actually ruin the experience? And why personalization seems to be the literal secret sauce for making humans trust a machine?
So to understand where this tech is going, I think we have to look at the foundational architecture that we're basically trying to escape.
Oh, for sure, the old school stuff.
Right, because before an AI could even pretend to feel anything, developers essentially had to manually build a respiratory system in code.
Which sounds exhausting.
It was. They used SSML, which is Speech Synthesis Markup Language.
Yeah, I was reading through the Amazon Poly developer guides on this, and the level of manual control is, it's fascinating, but it's incredibly tedious. They have this specific SSML breath feature.
Right, the Amazon breath tag.
Exactly. You literally use a tag to insert respiratory sounds into an audio file. So if you're coding an audiobook, you don't just paste the text in. You have to tell the system exactly how and when the narrator should breathe.
And the mechanism behind it is entirely deterministic. The documentation actually outlines 3 different modes for this.
Right.
So manual mode is the most basic. You explicitly drop a tag into the text string, and you define the duration and the volume of that specific breath.
Just hand coding every gasp.
Exactly. Then there's automated mode,
Mm.
which uses grammatical markers like commas or periods to algorithmically trigger a breath file automatically.
Okay, that makes more sense.
But the most complex one is mixed mode. So a developer might use automated mode for the baseline pacing of a whole paragraph, right? But then they manually override it with a heavy specific gasp tag right before a dramatic reveal.
And the guides point out how drastically these acoustic cues change the semantic meaning of a sentence for the user. If you program rapid, shallow breathing tags between words, the listener perceives urgency or panic.
Yeah, it completely changes the vibe.
But if you draw out the duration of the breath and lower the volume, suddenly the listener perceives contemplation. It's crazy. And older systems relied on these massive arrays of manual parameter manipulations.
Adjusting pitch semitone by semitone just to simulate happiness or anger.
Which is why I kept thinking of it as a digital marionette.
Oh, that's a good way to put it.
Right, because you have a developer standing behind a curtain, basically pulling strings to make the vocal cords tighten or the synthetic lungs expand. But my question, from a UX standpoint, is whether this deterministic string-pulling approach can ever actually trick the human brain into feeling a connection.
Or are we just building a slightly better customer service bot?
Exactly,
Right.
because it feels like an illusion that's bound to break.
Well, the architecture fundamentally hits a ceiling there. Because the machine isn't experiencing urgency. It's just executing a command line that points to an MP3 file. In a purely transactional context, like, asking for the weather or setting a pasta timer, the marionette approach works perfectly fine.
Because the user only needs clarity.
Right. But when that interaction transitions into a sensitive, high-stakes emotional context, the hard-coded approach just shatters.
And let's look at the data on those high-stakes contexts, because this is where it gets really relevant. There's been a massive boom in digital mindfulness and therapy. The 2026 meditation report shows that 60.5 million Americans are actively meditating right now.
That is a massive demographic.
Huge. And more importantly, therapy and companionship have actually surpassed productivity as the #1 consumer AI use case.
Wow, really?
Yeah, like Headspace's AI guide, Ebb, it has processed over 7 million messages. People are pouring their absolute hearts out to these systems. Yet there is a massive empathy gap documented in the UX research when people use synthetic voices for mental health.
Well, the limitation there lies in the acoustic inflexibility. Like SSML-driven voices score incredibly high on intelligibility. You can understand every single syllable perfectly.
Right, they're super clear.
But studies consistently show they score horribly on naturalness and emotional expressiveness. They simply can't micro-adjust to the tone of the conversation the way a human therapist naturally would.
But the research indicates it's even deeper than just a lack of acoustic microadjustments. There's an actual psychological barrier. I was looking at a user experience study published in Internet Interventions a few years back.
Oh, the labeling effect one.
Yes. The researchers designed an AI voice that was trained so thoroughly, it was acoustically indistinguishable from a human mindfulness guide. Like, the audio was, for all intents and purposes, completely perfect.
Indistinguishable.
Right. However, if the users were explicitly told the voice was generated by an AI, their acceptance scores plummeted. They rated the experience significantly lower than users who believed they were listening to a real person.
That is just a classic demonstration of the labeling effect. It proves that the empathy gap is a cognitive problem, not just an engineering one. Our brains possess this inherent skepticism toward a machine that's trying to soothe us.
Think about the last time you called a helpline and realized you were talking to an automated system. I mean, your guard instantly goes up.
Oh, absolutely.
The emotional resonance just evaporates because you know there is no organic consciousness behind the comforting words.
And if perfect audio alone can't bypass that cognitive labeling effect, developers logically try to anchor the voice in the physical world.
Right, so the intuitive UX fix is embodiment. If the voice feels hollow because it's coming from some faceless app on your phone, wrap the code in a physical body. Give the user something tangible to project their empathy onto.
But the data on this is wild.
It really is.
Because the physical embodiment strategy actually creates a massive trap. There was this human-robot interaction study from 2023 that tested this exact hypothesis, specifically in mindfulness meditation.
And they tested different voices, right?
Yeah, they deployed various text-to-speech voices, like a feminine one, a masculine one, a childlike one, and tested them against real human voices across 3 different physical setups.
Right, so condition 1 was just an audio player on a screen, so no physical agent at all. Condition 2 was a standard smart speaker, like an Alexa. And condition 3 was a socially assistive robot named Blossom.
Which is designed with, like, soft materials and physical movements to look cute and engaging.
Super approachable.
Exactly. And the hypothesis was that the socially assistive robot would ground the synthetic voice and make it feel more natural. But the results proved the exact opposite.
It blew my mind.
When the feminine TTS voice was placed inside the physical moving robot, users rated it significantly worse than when the exact same voice played out of a faceless screen.
From a design perspective,
Yeah.
this is the visual uncanny valley just brutally clashing with an acoustic reality. Because when you look at a flat app interface, your brain's expectation is pretty low. You expect a flat synthetic voice.
Right, it matches.
But when you look at a socially assistive robot moving its head, trying to simulate life, your visual system writes a check that the audio system cannot cash. Your brain expects a dynamic biological voice to emerge. And when the robot opens its mouth and a flat marionette-style voice comes out, the cognitive dissonance is just jarring.
The researchers actually noted that the visual presence of the robot functioned almost like a magnifying glass for the voice's artificiality.
Oh, that makes perfect sense.
Users literally described it as heavily emotionless. And furthermore, there was actual mechanical interference.
Wait, what do you mean?
As the robot attempted to physically mimic breathing or head tilts, the whirring of its internal servomotors audibly layered over the synthetic voice.
Oh, no.
Yeah, the physical mechanism of the robot literally masked the acoustic attempt at calm.
So slapping a piece of code into a cute moving robot doesn't bridge the empathy gap at all. It detonates it.
Completely backfires.
Which means the only path forward is to rip up those old SSML tags and rebuild the voice itself from the ground up.
Mm.
But how do you program something as fluid and messy as human hesitation without hard-coding it?
Well, you have to abandon categorical emotion entirely. And this is where the industry is shifting toward these advanced frameworks, like PeriEvits.
Okay, so break down the mechanics of PeriEvits for us. How does it actually move past the SSML tags?
So historically, a developer selected a rigid emotional label, right? Like sad. But human emotion is a spectrum. It's not a toggle switch. So PeriEvits utilizes a mechanism called PeriClap.
Which stands for?
It's a contrastive language audio pre-training model. And contrastive learning works by feeding the system massive pairs of text descriptions and audio clips. The system learns the mathematical relationship between a natural language prompt and the subtle acoustic features of the audio.
So instead of just selecting sad from a drop-down menu, a developer can type a highly specific prompt, something like, speak with nervous hesitation and a slight catch in the throat.
Precisely. And then the system uses a diffusion model to actually generate the audio.
Like the image generators.
Exactly like that.
Mm.
Think of a diffusion model like starting with pure acoustic static, just white noise. The AI uses the text prompt to iteratively carve away the frequencies that do not match the mathematical signature of nervous hesitation.
Wow.
It sculpts the static until you're left with the precise acoustic shape of that complex emotion. So it dynamically controls things like jitter and shimmer without the developer ever touching a manual tag.
I want to pause on jitter and shimmer for a second because understanding how these function is crucial for you guys listening. Jitter is the microscopic variation in the pitch of a voice from one sound cycle to the next.
Right.
And shimmer is the microscopic variation in the loudness or the amplitude. So when your voice cracks because you're holding back tears, that is an extreme spike in both jitter and shimmer.
Spot on.
And PeriEvits is manipulating those micro variations dynamically just based on a text prompt.
It is. But the data on generating these features reveals a really fascinating limitation. The AI struggles significantly to synthesize the emotion of happy consistently.
Wait, really? Why is happiness harder to fake than sadness?
It all comes down to acoustic baseline and arousal levels. Happiness is a high arousal emotion, and it's characterized by rapid pitch variations. Depending on the initial acoustic state that the generation starts from, the AI's attempt to synthesize the jitter and shimmer of happy often bleeds into the acoustic footprint of panic or like manic urgency.
That's what sounds crazy instead of joyful.
Exactly. Listeners frequently misinterpret the synthetic happiness because the margin for error in high arousal acoustics is incredibly narrow. But sadness, which is low arousal with suppressed jitter, is much easier to map mathematically.
Okay, this diffusion mechanism is incredibly impressive, but I have to challenge the core philosophy here.
Go for it.
If the AI is just taking a text prompt, looking at a mathematical map, and sculpting white noise to match the acoustic footprint of a sigh, is it actually becoming more empathetic, or is it just becoming a much more sophisticated sociopath?
That's the big question, isn't it?
Right, because it's mimicking the biological causality of human connection without actually understanding the emotion at all.
And that tension is the central debate in human-computer interaction right now. Does empathy require a biological origin, or is it defined strictly by its functional output?
Meaning the result is all that matters.
Right. System architects argue that if the perfectly modulated jitter-controlled voice successfully lowers the user's heart rate, then the underlying mechanism is totally irrelevant.
I just struggle to see how a purely functional approach plays out for the actual users, especially the demographic adopting this technology the fastest.
You're talking about the older adults.
Yes.
Right.
Let's look back at the 2026 data. The fastest growth in digital meditation is among older adults, a 4.2x growth rate. And according to socio-emotional selectivity theory, or SST, older adults prioritize emotional stability, reassurance, and predictability.
They do not want novelty.
Exactly. If a diffusion model is constantly shifting its jitter, shimmer, and pitch based on dynamic prompts, that sounds really erratic. It sounds like the absolute opposite of a calming, stable presence.
And that erratic variability is exactly what the Moon framework was engineered to solve.
Okay, so let's get into Moon.
Right. Moon, which stands for Model, Observation, Optimization, and Nurture, is a system architecture designed specifically to govern these advanced generative voices for older demographics. It basically puts guardrails on the diffusion model.
Walk me through the mechanics of the observation and optimization phases. Like, how does it actually detect and respond to a user's emotional state without being erratic?
Well, it operates as a continuous closed-loop telemetry system. So in the observation phase, the voice user interface, the VUI, isn't just parsing the user's words. It's actively measuring the acoustic latency between their
So
syllables.
it's listening to how they speak.
Exactly. It's tracking the user's own jitter and shimmer. And if it detects, say, an increase in vocal wavering or prolonged pauses, the system flags a state of anxiety.
Okay.
The very moment that flag is triggered, the optimization phase executes. It instantly restricts the generative model, forcing it to lower its pitch, soften its amplitude, and reduce its speech rate down to exactly 150 to 200 words per minute.
That is so specific. Why 150 to 200?
Because cognitive research identifies that exact range as the optimal processing speed for older adults in distress.
Wow. So it is reading the acoustic room and acting as an empathetic mirror. But for me, the nurture phase is where this architecture actually shifts from a reactive tool to a system that genuinely feels trustworthy.
Yeah, the nurture phase is fundamentally a memory storage mechanism.
Right, because a standard AI starts with amnesia every single time you boot it up.
Exactly. It only exhibits reactive empathy, meaning it only slows its speech rate after it measures your anxiety. But the nurture phase takes the data from the optimization phase, like registering, that slowing down to 160 words per minute successfully stabilized your voice, and it builds a longitudinal acoustic profile of you.
So by the 10th interaction, it isn't waiting for you to get anxious. It greets you at that slower, calmer cadence right out of the gate. It transitions from reactive empathy to anticipatory empathy.
It maps the user's emotional topography over time,
Mm.
which dramatically reduces the cognitive load on the user. They no longer have to guide the machine anticipates them.
Anticipatory empathy is so powerful, but it still relies on the system deciding what is best for the user. What happens when the user is given direct control over those acoustic parameters?
That changes everything.
Because when we synthesize everything we've covered today, the shift away from the old SSML tags, the failure of physical robot embodiment, and these advanced frameworks like PeriEvits and Moon, the ultimate bridge over the empathy gap really seems to be personalization.
And the HRI embodiment study we discussed earlier proves this unequivocally in its second phase.
Oh, right. I forgot about phase 2.
Yeah, so the researchers brought users into the lab and provided them with an actual physical control panel. They allowed the users to manually manipulate the text-to-speech engine themselves.
Wait, they gave them the dials?
Yes. The users could adjust the baseline pitch, fine-tune the speaking rate, and even dictate the exact length of the pauses between sentences until the voice sounded perfectly soothing to their own unique preferences.
The outcome of that manual tweaking was just staggering. Those user-personalized TTS voices didn't just outperform the standard AI voices, they achieved acceptance scores that were practically identical to the highly rated actual human therapists.
It's incredible. A machine voice, when fine-tuned by the listener, was literally as effective as a human expert.
The mechanism of success there is basically bypassing the one-size-fits-all design flaw. I mean, a voice that sounds deeply soothing to one person might sound totally patronizing or unsettling to another based on their cultural background or past experiences.
Exactly. Personalization ensures the acoustic signal is perfectly calibrated to the user's specific psychological baseline.
And we see this validated at real-world scale in the 2026 meditation statistics. When users interact with these compassionate tonal AI sessions that have been specifically customized to their acoustic preferences, the completion rate for the therapy session hits 70%.
That's a huge metric.
Right. But when users are forced to use the standard default AI voice, the completion rate drops to just 32%.
That massive delta in retention proves that forced adaptation fails. When the system adapts to the specific acoustic needs of the human, the cognitive friction just disappears.
It fundamentally changes the user experience because personalization grants agency. When you tweak the voice to your own preference, you are no longer receiving an artificial imposition from some faceless corporation.
You're projecting your own comfort onto the machine.
Yes, you become a co-creator of the interface, and in doing so, the fact that the voice lacks biological causality just ceases to matter.
The user's active participation in designing the voice overrides the cognitive labeling effect that normally causes us to distrust machines.
It is truly a remarkable evolution. I mean,
Right.
we started today by looking at developers pulling strings behind a curtain, manually coding Amazon:breath tags into rigid digital marionettes.
And we saw how trying to mask that rigidity by stuffing the voice into a whirring, socially assistive robot only triggered the uncanny valley and shattered the illusion.
Which basically forced the leap into generative acoustics. We unpacked how frameworks like PeriEvits use contrastive learning and diffusion models to sculpt white noise into precise paralinguistic features, like jitter and shimmer based entirely on text prompts.
And we explored how the Moon framework governs that generation for older adults, measuring acoustic latency to shift from reactive adjustments to longitudinal anticipatory empathy.
All of which points to the reality that giving the user agency to personalize the voice is the ultimate secret to building trust. But as we wrap up, I want to leave you with a final thought regarding the nature of this technology.
Let's hear it.
We established at the very beginning that a synthetic voice lacks the biological causality of a human. There are no vocal cords tightening. There is no actual emotion driving the acoustic signal. But if a machine uses a diffusion model to perfectly mimic the micro variations of a sigh, and it uses longitudinal memory to anticipate your anxiety before you even speak, and if the result of that interaction is that your heart rate drops, your panic subsides, and you feel genuinely comforted, does the biological causality actually matter?
That's a deep one.
If the physiological benefit to your body is undeniably real, is a perfectly engineered acoustic illusion just as valuable as the real thing?
Honestly, the answer to that question will probably define the next decade of human-computer interaction.
I totally agree. Think about that the next time a digital interface asks you how you're feeling today and actually seems to care about your answer. Thank you so much for joining us on this deep dive into the source material. We will see you next time.